I am Richa Islam from Mathabhanga College, Chemistry Department. The topic I will discuss today is 3,3 Sigmatropic Rearrangement. First of all, I will say something about sigmatropic rearrangements. A sigmatropic rearrangement is defined as migration in an uncatalyzed intermolecular process of a sigma bond adjacent to one or more pi systems to a new position in a molecule, with the pi systems becoming reorganized in the process. Types of sigmatropic reaction. Various types of sigmatropic reactions are Glycine reaction, Cope reaction, Oxy-Cope reaction, 2,3 sigmatropic rearrangement, 3,3 sigmatropic rearrangement, 1,3 H shift, 1,5 H shift, 1,3 C shift, 1,5 C shift. Sigmatropic is differentiated by assuming that there will be a migration of a sigma bond. So, where the migration will take place, pi system will be migrated. First, let's see how 1,3 sigmatropic is named. In first naming, the word symmetry we will give it in such a way that there is sp3 carbon numbered in two directions from there. 1, 2, 3 hydrogen will be 1. This rearrangement is carbon hydrogen sigma bond will be migration number 3 carbon and sigma bond will creates making will attack hydrogen. Number 1 hydrogen has migrated to the number 3 carbon. Finally, new bond from 1 to 3. So this is called 1,3 sigmatropic rearrangement. The next molecule. sp3 sigma bonds from carbon hydrogen sigma bond will migrate, then will break, then will numbering, so finally migrated carbon 5 hydrogen 1. This is called 1,5 rearrangement. This is called 1,5 sigmatropic rearrangement. So the next molecule sp3 bond will break, sp3 did 1. 17 new sigma bond migrated will number 7 carbon. So this is called 17 sigmatropic rearrangement. And the next molecule. This is a heteroatom. sp3 carbon, sp3 heteroatom will be sigma bond migrated. sp3 bond will migrated. Pi bond migrated number 3 carbon. So 2,3 position sigma bond will migrated. This is called 2,3 sigmatropic rearrangement. Similarly, the molecule sp3 carbon is 1,1, 2,3 on two sides. Finally, this sigma migrated 2,3 and 3 new bond from number 3 carbon and number 3 carbon. So this is 3,3 sigmatropic rearrangement. These are the various types of sigmatropic. Now, the main topic I will discuss is the 3,3 sigmatropic rearrangements. The Glycine rearrangement was the first to be discovered. The original sigmatropic rearrangement occurred when an aryl ether was heated without solvent and an orthoallyl phenol resulted. This is the Glycine rearrangement. The first step in the reaction is a pericyclic reaction of a type that you will learn to call a 3,3 sigmatropic rearrangement. So this is a one-step mechanism without ionic intermediates or any charge. Just like a cycloaddition, the arrows go around in a ring. The difference between this and a cycloaddition is that one of the arrows starts on a sigma bond instead of on a pi bond. The second step in the reaction is a simple ionic proton transfer to regenerate aromaticity. The aliphatic glycine rearrangement also occurs. This particular reaction is called a 3,3 sigmatropic rearrangement because the new sigma bond has a 3,3 relationship to the oldest sigma bond. You can see this if you number both ends of the old sigma bond 1 and count round in both directions to the ends of the new sigma bond in the product. I will find that the ends of the new sigma bond both have the number 3. These 3,3 sigmatropic rearrangements happen through a chair-like transition state which allows us both to get the orbitals right and to predict the stereochemistry of the any double bond. The orbital looks something like this. Orbital descriptions of 3,3 sigmatropic rearrangements. It is possible to give a frontier orbital description of a 3,3 sigmatropic rearrangement, but this is not a very satisfactory treatment because we don't have two separate regions reorganizing each other across space as we did in cycloadditions. There are three components in this reaction: two non-conjugated pi bonds that do have to overlap across space, and a sigma bond in the chain joining the two pi bonds. The Woodward-Hoffmann rules give a more satisfying description, and we shall follow the routine outlined on P892 for cycloadditions. Notice that for staticity, we can use the three-dimensional diagram we have already made. The Woodward-Hoffmann rules: in a thermal pericyclic reaction, the total number of 4q plus 2 and 4r components must be odd. Number 1. Draw the mechanism for the reaction. We shall stay with a familiar one. Number 2. Choose the components. All the bonds taking part in the mechanism must be included and no others. Number 3. Join up the components where new bonds are to be formed. Make sure you join orbitals that are going to form new bonds. Number 3. Label its components or a depending whether new bonds are formed on opposite sides. See below for the sigma bond symmetry. The direction of 3,3 sigmatropic rearrangements. Orbital symmetry tells 3,3 sigmatropic rearrangements are allowed but says nothing about which way they will go. They are allowed in either direction. So, why does the Glycine rearrangement always form the carbonyl containing product? Think back to our discussion on enols, and you may recall that the combination of a carbonyl group and a carbon-carbon sigma bond made the ketoform more stable than the enol form with its combination of a carbon-carbon pi bond and a carbon-oxygen sigma bond. The same is true here. It is the stability of the carbonyl group that drives the reaction to the right. Applications of 3,3 sigmatropic rearrangements using other elements. There is no need to restrict our discussion to carbon and oxygen atoms. We shall finish this section with two useful reactions that use other elements. The most famous synthesis of indoles in the Fischer-Indol synthesis, and we can now look in more detail at the key step of this remarkable reaction. Condensation of phenyl hydrogen with a ketone in slightly acidic solution gives a phenyl hydrogen. This reaction, if the ketone is enolizable, this imine is in equilibrium with the corresponding. The important bonds are given in black in the diagram. The enamine is ideally set up 3,3 sigmatropic rearrangement in which the sigma bond to be broken is the weak NN sigma bond, and one of the pi bonds is in the benzene ring. In this reaction, the product is a highly unstable double imine, but aromaticity is immediately restored and a series of proton shifts and carbon-nitrogen bond formation and cleavage reactions give the atomic indole. Reaction is that was a 3,3 sigmatropic reaction involving two nitrogens. There follows one wheel, two oxygens and a chromium atom. Then tertiary allylic alcohols are oxidized within acid solution. No direct oxidation can take place, but a kind of conjugate oxidation occurs. The last reaction is the first step in chromium oxidation can take place to give a chromate ester, but this intermediate has no proton to lose, so it transfers the chromate to the other end of the allylic where there is a proton. The chromate transfer can be drawn as a 3,3 sigmatropic rearrangement. The final step is the normal oxidation in which chromium drops down from chromium 6 to chromium 4 and eventually by disproportionation to green chromium 3. Thank you. Have a nice day.